Hello, class. Okay, that's better. It seems that I am recording now. Isn't that interesting? Because I just looked at. I always look at that thing, and I thought, well, I think I see the green on there, but then it wasn't. Actually, my on cable switch had been punched or something because I got too close to the table or something. And anyway, that's what happened. So today, what I want to do, we're working on our last large topic, I should say. And that's going to be Flexure, the Flexure equations. We're going to bring the shear force and bending moment diagrams that we learned in statics, as well as centroid, understanding, because that's all used in this too, as well as moments of inertia. So everything's going to be, used in this today. I'm not going to write all those down because I'm going to basically show you what they are in a few minutes anyway. So what I want to do is I want to look at, I think I'll do two like this. I'm going to look at a beam, and I'm looking at the cross section of the beam right now, right? So I'm looking at the side of it. How could I really draw this? In fact, yeah, I could just draw it, like a 2 by 12 or whatever, right? I'm just going to draw this three-dimensional. I won't draw the other one three-dimensional because I don't trust myself in drawing it that well three-dimensionally. However, what I'm going to do now is I'm going to put just a square on the side of this, and I'm going to label that square. Let's say the square is right here. I'm going to label that square as A, C, E, F, B, D. I can put it up there anyway. It's a B. B and D. I'm going to put a couple other ones in there, but I wanted to draw that larger. In fact, right down between here and here, I'll just put some points there where all of these A, C, E, F, and B, D are. But right in between there, I want to put another two, G and H. Okay? Now, I'm going to place a force on this. I'm going to exaggerate this, of course, but I'm going to place a force on this, a great force, P. And what that P is going to do, and you might want to think of this as like rubber or plastic or whatever, but because literally everything is elastic that's in the elastic range. But now what I'm going to do is I'm going to redraw that after it's been deformed. Oh, that should have gone up there by P. All right, let me just make sure I can sort of get that. There you go. All right, so now P is being placed on it. It's being pushed down. Obviously, you can see that it's going to, if it's supported here and it's supported here, and that's not drawn to scale and is 4,000 feet long, you can see that it's going to bend. Actually, even under its own weight, I'm sure it would bend. Now, what I want to do is I want to look at those four places again, right? Because now this is A and this is C, right? But the thing has now bent in such a way as to extend B and D. So I'm just going to draw a line through here that would go through both of those. And then this point down here is B. This point is D. And then the 2 points in the middle that we had, E and F, right, are still there. And then B and D are down here. So, if I was to take a parallel to this line, in fact, let me get my glass. This is why I have the glass one. So that if I took of parallel, yeah, this is why engineers use glass rulers. Just exactly for this reason, so we can actually see through the ruler. We like to be like Superman, right? So X-ray vision doesn't come in hand, it doesn't work, so we're going to actually, and I didn't do that really well either. I could have done it better, but that looks pretty parallel. So now I'm going to call this angle that I've got right here, I'm going to call that d theta. Okay? And I think everybody sees what we've got here. If I was to take this area right here, in fact, this angle right here, if you think about it, this angle right here, I'm going to draw it right on this larger drawing. That angle is also d theta, isn't it? Because I've got two parallel lines with a line crossing that line. So I know that this angle here has to be the same as this angle here. Does everyone see that? In fact, why don't we blow up just this section right here so that we can see that section a little better? And you know, we'd also have H right here, wouldn't we? Because we'd have G right there. And then actually H would be over on the other side here, wouldn't it? That would be, this would be H prime. And, oh, wait a second. No, I defined that. Have I defined H? I did. Well, I'm gonna, okay, that's fine. That's fine, because I'll just use H prime. So that's H. Okay, so this would be H because this is over here, and this would be H prime that's down here. But basically, they're both at the same distance from this point, aren't they? And we know that that angle is d theta. So that angle is d theta. Now, where's my neutral axis? Well, my neutral axis is where there's neither compression nor extension, right? So it's right at E and F. That's my neutral axis. Now we don't know, I haven't derived yet that the neutral axis is actually at the centroid of the cross section, right? I haven't derived that yet. I'm just saying that the neutral axis is somewhere in that cross section, right? I haven't actually defined it yet as you know, being at the neutral axis, but we'll show that it has to be in just a second. So let's go back to this, and in fact. Okay, I've blown all of these things up. I think everybody is, in fact, what I want to do is look at two congruent triangles. And so I'm going to be looking at two congruent, I shouldn't say triangles, I should say arcs. This arc right here, and this arc down here, which is, of course, this arc right here, isn't it? Okay. So, you know, everybody can see what we've got there. So what I want to do is I want to go down to look at what the strain is at any location. And G and H is just, you know, any location really. So just looking at the distance of G and H, and looking at this triangle that I've got right here too, which is H to H prime, right? That distance right there also is subtended by an angle d theta. All right. Now, what is that distance? Let's look at the distance that we've got now. I'm going to draw another line. I'll make it green. I'm going to draw another line down here that's at GH, right? The GH is not at the neutral axis, is it? No. GH is separated from the neutral axis by a distance of y. Does everyone see that? That y? That distance between here and there is y. You know, if I look on here, wouldn't this distance also be y? Right, does everybody see that? So that distance from whatever the neutral axis is down to here is y. And so I'm getting the various different points. And of course, this distance right here would be the distance from h prime to h, the extension. You could say that this is really, right, my extension. And what would the original length be? The original length would be at the neutral axis e to f. That's my original length. And then my delta, right, my extension is going to be h prime to h. So let's look at the strain, right? We know that the strain is the extension over the original length. So we could say that it's going to be h prime to h over e to f. Well, if we look at h prime to h, this distance right here, what is that? That would be y d theta. Y d theta. And I hope I don't have to remind anybody that whenever we're talking about, you know, our arc length, S, if we know that it's a radius 0 and it's an angle of theta, then the distance S is equal to R times theta. And that's all I'm using here. I'm just saying that this is my extension, that's delta, y d theta, and then what's this original distance here? Well, that would be, let's call this whole distance right here, I'm going to call that rho. You know, we use rho for radii and stuff, and that is the radius that I've got right here, isn't it, for this congruent triangle? And so that's what I've got down here. I've got rho d theta. So strain equals y d theta over rho d theta. Did you see anything we can cancel out? That's right. So I've got y over rho. All right. I don't think anybody, you know, has any problems with that. Now, I'm going to end that there, and I'm actually going to move down here underneath it for the next step, because I think that it goes together. Might use that for drawings or whatever, but what is sigma, right? So this is epsilon sub x. Let's get our things. This is my x-axis along the axis of the beam, right? So if that's my x-axis, then this must be my y-axis, right? And this must be my positive z-axis. So that's my y, that's my x, and that's my z. All right? Okay. So let's look at the stress in the x direction, because we've looked at the strain in the y direction, and we know that the stress in the y direction and the strain in the y direction, we know from the stress strain curve that we've been working with, right? And we only use the elastic area, remember, which is a straight line, linear relationship. So we know that that Hooke's law, the slope here is going to be E. So this equals E times epsilon, right? All right. And we got epsilon sub x. And we already have an equation for epsilon sub x, so we know that this is just going to be E times Y divided by rho. Now, I could write this another way too, couldn't I? I could write sigma over Y equals E over rho. That's a rho. Okay. We're just going to keep that for later. I'm going to put a line underneath this. We're going to put that in the oven to bake for a little while, and we're going to come back to that. But what I want to do, because they're, important equations, is I want to circle this equation, because we're going to come back and use that before we finish the whole derivation of the Flexure formula. All right? Now, let's keep going. Let me have a sip of tea. Oh, that's delicious. It looked delicious, and it was delicious. So anyway, now we've looked at this in this way, but now what I want to do is I want to look at the beam end on. I want to look at it like this, right? Let's say that I'm looking at the end of the beam. And now I look across it, and I see that this is my z-axis. This is my y-axis. I'm going to draw the axes all the way through, as I've done with that too. And then coming out of that is going to be my x-axis, right? Now, what have we really got here? What are we really looking at? We're looking at forces working in the beam, right? And we know that there's going to be stress in the x direction. I mean, we're assuming. That's why I'm doing this whole thing, to show you that there are stresses in the x direction. But that's the question that I have. How would those stresses manifest themselves? Well, to have stresses in the x direction, we have to have forces in the x direction, don't we? And so if I was going to look at a small little cross section here, right? Let's say that that little cross section that I'm looking at is dA, right? And now I'm going to have a force that's pushing, right, in that direction. And if I've got a force that's pushing in that direction, what is that force? Well, isn't the force just equal to the stress times the cross-sectional area? In fact, couldn't we just find out what it is for that little small cross-sectional area and then integrate it across the entire cross-section of the beam that we have? I'll just cross-section that out real quick, make it look nice. I am not an artist. Right. So I obviously went into the right field then. But I've got my little dA. dA times the stress is going to give me the force that's working there. Now, why am I so interested in knowing what the forces are that are working there? You know what? This is not moving, is it? It's not moving. Not moving. Even if it's doing this, it's not moving. So I know that the sum of the forces in the x direction have to equal 0. So the sum of the forces in the x direction have to equal 0. Well, if that's true, sum of the forces in the x direction, have to equal 0, then that means that if I integrate over the entire area, right? If I integrate over the entire area with sigma dA, right? Because sigma sub x dA, then that should give me, and it should equal 0. right? So if I sum over the entire area, because the forces have to equal 0, it's not moving, it's in static equilibrium. So if I sum over the whole areas, that's still going to equal 0, isn't it? Well, let's substitute that in. Let's substitute in what we know for sigma with that. That would be EY over rho. So what we can say is that the integral of EY over rho dA has to equal 0. Well, you know, is there any constants there? Well, that's the modulus of rigidity, right? And that's a rho. Well, that's the whatever the radius of curvature of the beam. So those have to be finite positive numbers. Finite positive numbers. So and they're constant, so we can take them out. E over rho comes outside of the integral, and then what we're left with is y dA. Y dA. Where have I seen the integral y dA before? And I know what you're saying. You're saying that's a centroid, right? That's why we learned centroids in statics, because we were eventually going to get to strength of materials and we had to know them. And we know that the total cross-sectional area times the centroid of that cross-sectional area equals the integral of the individual centroids of all of the area, the small differential areas. That is our relationship, isn't it? So can't I say that E over rho times the total cross-sectional area times the centroid of the cross-sectional area has to equal 0? Yes, I can say that. You know, I bought these new pens today for like $24, and I thought, because, you know, I needed some Sharpies, and I thought, well, it's got to be the best deal, right? You know, how can you tell how much ink they put in these? I mean, I've only used this for like half a lecture, and it's already running out of ink. But I got 24 of them for $20, so it should take me through at least another 20 lectures. Should be no problem. All right, let's keep going with this then. So let's look at these. Can E is a finite positive number. Rho, finite positive number. How about A, total, the cross-sectional area of this? The total cross-sectional area, is that going to be a negative number? No, it's going to be a positive finite number. This can't be 0. The radius of curvature, because I've loaded it down, has to be some positive number. This is always a positive constant. So the only thing that can be 0 in here is y bar. And what I'm saying is the distance, right? The distance from the neutral axis to the centroidal axis equals 0. Let's circle that. That is so important, isn't it? This is the result of what we've just done. We've just proven that the neutral axis has to be the centroidal axis. So this is my centroidal axis, right? And it also is the neutral axis, because the neutral axis is the centroidal axis. So do you see why we learned how to get centroids? Because we have to find the centroid to find the neutral axis, don't we? That's right. And so that's why in mechanical engineering, that is so essential to understanding the centroids in statics. And boy, I'm not getting my life out of these Sharpies. So anyway, the neutral axis, the centroidal axis, one and the same. We've proven that. The second thing that I want to look at is I want to look at the moments. Now, we've still got the force. We still know what the force is, right? But now I want to look at the moments, right? The moments about the y-axis. So is anything flexing about the y-axis? I mean, as I load this beam, you know, that's why we've got this rectangular cross section. Here's something. What if I had instead something that was like this? The cross section of a beam that looked like this, that only had one side that was supported, right? And then you're putting weight on top of this, but I only have one side here that can sort of do that. Now where's my y-axis? My y-axis would be like right down through the center here. But as this thing is loaded up, since I only have a support on this side, don't you think that this would tend to start to buckle? That this would start to have rotations down here, right? That this flange here? That's right. That's why what I'm going to show you right now is why we don't make things like this. We make things predominantly symmetrical about the y-axis, right? An I-beam is symmetrical about the y-axis usually, and that's so that we don't get any moments about the y-axis. So what I'm assuming is that the moments about the y-axis are going to equal 0. And how do I make sure of that? Well, there you go. So this is the y-axis right here. What's the distance, right? What's the distance from the y-axis along this cross section that I've got? I should use another pen color. I'll use blue. What's the distance? So the distance is going to be this distance, isn't it? About the y-axis. Isn't this perpendicular to the y-axis? That would be the distance that we look at, and that would be z. So when I'm looking at my moments of inertia about the y-axis, it's really the distance z. We know those have to be equal to 0, so we know that the integral of z, that distance right there, times f, right? dA, well, no, I shouldn't put dA there. I'm just going to put f. And actually, I put df there too, but I can exchange that in a second, which I'm going to do, because what is f? F is really sigma sub x times dA, right? So my real integral that I have here is z times sigma sub x dA. And I'm integrating over a anyway. You know, here was f, but, you know, whatever. We don't have that. We have a, so we can do that, and we've got sigma sub x, right? So why don't I replace sigma sub x with what we've calculated sigma sub x is up here, right? Where did I get that? Sigma sub x is, you know, I probably should circle that too, because we've used that once. I'm now using it again. I'm going to use this in a second. It's all the same equation, but you know, I just want you to see what's going on. So if I then replace this, I end up getting z times y times e all divided by rho. And once again, I'm just going to put a little line here so that we can use this. And then again, I can take e and rho out of the equation, and I end up having yz dA. You know, I forgot the dA here, dA, right? YZ dA is called the product of inertia. That's called the product of inertia. And basically what it's saying is, if you don't want, if you don't, and that's 0, of course, because we started with 0 up here. If you don't want any rotation around the center, you should make whatever beam you've got symmetrical, so that this is equal to 0. The product of inertia should be equal to 0. That's what this is saying. And the way to do that, of course, is to just make it symmetrical about the y-axis. So that's the second thing that I wanted to just bring out here. No, we're not done yet. There we go. This is the most important thing because we've looked at moments of inertia about the y-axis. So now I want to look at moments of inertia about the z-axis. And of course that, just using what we had before, is going to give me y times sigma sub x dA. And when we replace it with what y is, or sigma sub x is, what we end up getting is y squared, right, times E over rho dA. I think everybody can see what I can do with this. So the sum moments about z equaling 0 is going to be E over rho times the integral y squared dA. E over rho times I, right? Because the moment of inertia about the x-axis is y squared dA. So I'm just putting that in there, right? So that's what I get. So let's see, moments, all that. Oh, I just forgot to. Just a second. Let me check something. I'm back. I just wanted to check something and make sure that something was right. It took me a couple minutes, but I absolutely realized what the heck's going on. All right, now, this is my z-axis. If you want to look at the z-axis there, did I draw it someplace else? Yeah, the z-axis here. So we know, since the z-axis is the centroidal axis, that we're going to have just as much, when we look at it, just as much compressive force above this as tensile force below it, right? Because we're squeezing in the top. So up top, what can I use? I use this. Yeah. Up top, we have compression. And in the bottom, we have extension, right? So what that manifests itself as is compression is a negative stress, extension is a positive stress. Right at the neutral axis, we have no stress, right? I hope I'm recording on. Yeah, well, so I want to look at just what's occurring on the top of this. Let's just, where can I draw a picture? In fact, what I'll, yeah, I don't know. We're just going to look at, I'll just draw it a little thinner than it actually is. Let's say that's my neutral axis. We're just going to look at what is occurring the moment on the top where I've got positive compressive things. So some of the moments up top is going to be y. Well, we've done that. I can actually step to the next thing. The moment up top, I'll just do it. E over rho times I, right? I can exchange that, can't I? Because I know that up top, because that's going to be E over I could say, using this exchange here, E over rho is just sigma over Y, isn't it? And if I have that relationship, doesn't that also tell me that sigma, my stress in the x direction, is also, because I'm solving for sigma, is going to be the bending moment, right? The bending moment times the distance from the neutral axis to the centroid of the top part, right? That would be my distance y. Why do I always draw those around lines? There you go. Y. Well, that's even a worse y. That's y. Right? This distance right here is y. That's the centroid of the top part. And I'm going to have opposite forces, opposite stresses, negative stresses on the, well, actually, there's compressive. So this would be negative up top and positive down bottom. But whatever, they're going to be, as far as the two magnitudes concerned, they're exactly the same. So my, that's the distance from the neutral axis. Let me write that. Y equals distance from neutral axis to centroid of top. All right. Have I done that right? Yes. Over I. And I of x, of course, and yeah, that's for the full. Now, I of x is for the full cross section, right? That's for the full cross section. Now, this distance here, and when I say to the, it can be any distance. I probably should take that out. That is not to the centroid of this. It's any distance up here. I'm getting ahead of myself because I'm thinking about shear strain in the web. I've got to, you know, I'm thinking of deriving that for you guys next, but I can't give you too many lectures. So no, that is not to the centroid. That distance, I'm crossing all that out. It's late. Let's look at that. This is from the neutral axis to any point I want. If I want to find out the stress right here, that's why. If I want to find out the stress right here, that's why. If I want to find out the stress right on the outside, right, these are all y's. But the stress on the far outside, which is going to be the maximum, right? So my maximum shear stress is going to be MC, C being the distance all the way to the furthest outside over I. Oh, sorry about that. And the whole don't even think about that. I was thinking that's how we do it with shear strain and stuff. And I was getting I'm getting my two lectures confused at the very end of this one. All right, that is our Flexure formula. Then we've got. Let me just circle that. The maximum shear stress is going to be MC over I. That's why we've determined all of these. First, we've got to use our centroids. We've got to use my over I. Of course, that's not going to be the maximum because that could be anywhere in the cross section. That could be right here. It could be right here. The maximum is going to occur at the furthest distance away, isn't it? Does everybody see that? Okay, on to the next lecture.